So luckily, we don't always have to solve for the change with a quadratic, because if some certain conditions are true, we get to make this what is known as the simplifying assumption. Okay, so here's when you can avoid the quadratic. Okay. If these conditions are true, if your K value is very small. What do I mean when I say small? How small? We're talking about it needs to be times 10 to the negative fourth or less kind of small. What does it mean if K is a very small number? Does that mean the reaction is really turning into a lot of product? Or does it mean it's really mostly staying reactant? The second one I said, right? K is really small. It really is mostly this staying at this side of the equation, right? I'm saying it's not mostly products, it's mostly reactants. Left side. Yeah. It's mostly, if this is very small, it's mostly this side of the equation, the reactants, where it is. Okay. And the initial amount you're given, okay, any initial amount is relatively larger. So what am I talking about? A lot of times, if your initial concentration is around 10 to the negative 2 or larger, you're good to go with this assumption, okay? We are going to make what we call the simplifying assumption. Simplify. Too many vowels in that word. What we write, and this is what I need you guys to write. If you do this on a problem, if you do this assumption on one of your problems for like show your work, right? I need you to write on the problem that you made this assumption. This is what you should write. This is what we write, okay? We're going to assume X is small. That is the assumption we're making. What this means is that in a subtraction or an addition, what are we saying? X is too small to what? Make any difference. X is just too small. Doesn't matter when I'm subtracting it or adding it. It's too small. Doesn't matter. It's too small. Like what? Here's an initial. If I had a 1 molar, right? And I subtract 2 times 10 to the negative third. Let's say that was my X. Yeah. Let's say that was my X. What am I doing? 1.00 minus 0.002, right? That's what I'm saying. Guys, what is this answer? Not addition, subtraction. Isn't it still basically 1? Yes. This is too small to really make much of a difference. That is what we're assuming here, okay? Does that mean I can ignore x when I'm doing multiplication? I can only ignore it in a subtraction or an addition, okay? So let's say we could assume here, which we cannot, because why? Think about the 2 criteria I just gave you. My K value is pretty high. It's 4. It's not very small. And my initial values are also not very low. I mean, they are large, but they're too close to this. They're not far enough apart from each other. Okay. The difference is not big enough here. But if I could make that assumption, then in this 0.15 plus x, I would just be saying, well, it's really just 0.15. And if you make the assumption, you're saying, well, 0.4 minus x is really just basically going to be 0.4. That's what we're assuming. Okay. So let's see when you would use this.
So I guess it would be more benefit to find q to then know a. I went back to this, like knowing this was 1. Like it would be more benefits like to solve for q anyways, if we can't automatically tell.
Yes. Yes. Yeah. If you can't tell automatically, like if some things are 0, you should know automatically which way it's going. But if you can't tell, go ahead and solve for q. Yeah, that's to your benefit. Okay. When can you use this simplifying assumption? Again, anytime you have this criteria, but even if you're not really sure if you can use it, okay? What if it's kind of a close situation? Go ahead and do this assumption. It makes your life easier, right? This is fast. This is going to be faster. But what you have to do when you make this assumption, if you do this on a problem, you ought to check yourself at the end. Check yourself. Here's how you check yourself. We want to check your assumption with what is known as the 5% rule. Okay. You should check yourself whenever you do the x is small assumption. What you do is after you solve for x, take that calculated value of x that you found, and I want you to divide that by your given initial amount, right? You're given an initial amount in the problem, divide it. And then you can multiply it by 100, turn it into a percentage. If your answer here is less than 5%, or even equal to 5%, let's say even if it's equal to 5%, you're probably still fine. Then this was a valid assumption. It was fine to assume x was small. But if it's greater than 5%, you got to go back and solve for x using the quadratic.
How many times can you actually do this? Like in real life?
All the time. We do it almost all the time. Oh, hang on. Hi, Greg. I'm okay. I'm actually in the middle of finishing up my lesson, my teaching real quick. Can I call you? Okay. Okay. Thanks, Greg. Bye. That's my money manager. With all that money I have. I think some of y'all may remember this. I think I'm going to buy a new house. Y'all remember from the first semester when I went and got pre-approved and my phone was blowing up every day with all the, yeah, okay. So I kind of like let it chill out for several weeks, but now I started looking again and I think I'm gonna buy a new house. So on the outside, I haven't looked on the inside except for pictures. It's still here in California. Mm-hmm. It's a little bit bigger house, a little bit newer house. Okay. What numbers should we look at? In our in-class to practice this, we're going to look at 22 and 23. And I'm just going to do one of them right now. Because then I got to tell you one other thing that I forgot the other day. So let's see, which one do I want to do, 22 or 23? You want me to do 22? Just because you like to go in order, you hate it when I skip around like I do. I don't know that either one of them is harder than the other. Yeah, let's do 22. That works. Just 22 is good. Okay. So, yeah, I don't know. Formatting on this got all screwy. Okay. So this is still, I give you an initial, I give you a K. I'm asking for equilibrium concentrations, right? When you read the problem on 22. I give you an initial, I give you a K. I'm asking for equilibrium concentrations. That is type 3, right? Fill in an ice table. Here is an equilibrium. Now, this equilibrium is what we're going to study when we get to chapter 14. This is an acid equilibrium. HCN is an acid. Okay. So this actually should look kind of familiar. Doesn't this look kind of like when we learned how ionic compounds like split apart, right? That's basically what this is doing, but it's an equilibrium, yeah? And there's a K value. What do we notice about this value of K? Wow, it is so tiny, right? It is very, very tiny, very, very small. What do we notice about our value of the initial concentration? Way bigger than the K value. I think we can make our assumption here. Okay. Fill in your ice table. The only initial amount I was told was for the HCN, right? So that means H plus ion and the cyanide ion both are 0 to start, right? I wasn't told any other amounts. That's what I have to go by, which means the reaction is going to go in the forwards direction. Okay, so this is decreasing, and these two are increasing. So at equilibrium, there's my amounts. Write your K expression. K equals H plus CN minus. All of this is 1 to 1 to 1. 4.9. Because this is so small, we're going to assume X is very small. What does that mean? Where can I ignore X when I'm making this assumption? I can ignore that there's just an X here. I can ignore this subtraction of x. These two concentrations are still x and x, right? But what I'm saying is that here, 0.15 minus x, I am assuming that that is essentially going to just be 0.15. And this divided by this is going to equal my k value. So essentially, what is the math that I'm doing? X squared divided by 0.15 equals this. Y'all can solve for x now without using a quadratic, right? Right? Yes. So 0.15 times my k value, and then I'm going to take the square root of that, right? And we should get, I guess I forgot, let's see, because I forgot to write my answer on my sheet, so let's see. 8.6 times 10 to the negative 6. Yes, okay. X is very small, isn't it? What do I do now? Should I check? Let's check the 5% rule. When I say check the 5% rule, what am I doing? This value over that initial given amount. 8.6 times 10 to the negative 6 divided by 0.15. Checking. Times 100. .5%. So was this a good assumption, a fine assumption that we could make? Absolutely. Yes. Don't forget what the question is actually asking. I mean, we do all this to solve for x, but then be sure you read, what did the question actually ask for? I think it says, what are all the equilibrium concentrations, right? So what is the concentration of that HCN at equilibrium? It's basically unchanged, right? If I do 0.15 minus x, I'm still going to get 0.15, yeah? It is essentially unchanged. But my products have a concentration now, don't they? Is it a very small concentration? Yes. Does that mean I can ignore it? No, that's why we do this math. Molar. Oops. Molar. Molar, 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 molar. Okay. And then, like I said, I'm not going to work 23 here, but you guys could look at 23 in the slides if you want to. It's this with just different compounds. Okay. What I need to go back to was something in the previous set of slides. So I'm going back to, what would those be? 8, lecture 8 slides. And there was something else that I needed to share with you guys about just K, manipulating K. So this is jumping back into section 13.2. Okay. So this is 13.2 when we just learned what K is. What is K and what is Q? We learned that. Okay. We can actually take the value of Q given for an equation and we can manipulate it. Okay, we go. Here we go. Okay. We can manipulate Q. Do you guys remember from Gen Chem 1 when we learned about enthalpy and we had those equations that had the delta H next to it and we could manipulate the equation, right? We could like flip the equation and write it in reverse. Or we could multiply everything in the equation by 2 or by 3, right? Then when we did that, we had to do an equivalent change to the value of delta H. Okay, that was something called Hess's law. That rings a bell. Okay. We can manipulate equilibrium constant values as well, K values. Okay, so if we right, if I have a reaction, let's do a simple one like I have on the board. A goes to B, okay? And I'm writing K for the way it's written, right? In fact, let's be specific. I'm talking about going forwards, right? What does K equal? B over A, right? Let's just say I'm doing concentrations because that's what I like to think about. But thank you. Yeah, I mean, yeah, we're done. Yeah, we're done. I know. I said C, and I said my bad. Okay. What if I think about the reaction going in reverse, though? That's now my product, right? If I'm going in reverse, okay. A over B. What's the relationship between those two? They are inverse reciprocals. Yes. So you just need to know if you write a reaction in reverse, what should you do to the value of K that was given to you? Take the reciprocal of it, right? Look at number 11. Yeah, sorry, okay. We're jumping all back around. Look at number 11. Right? The forward and the reverse are reciprocals of each other, right? That's what we're saying. On 11, I said if K for a reaction is 0.0450, so this is specifically talking about pressure base, but it doesn't matter if it's pressure or concentration. forward direction is that value. What's the value if it's in reverse? 1 over that number. Yes. I got the number 22.2. Yeah. Okay. Reciprocals, forwards or backwards, reciprocals. Okay. The other thing you can do, huh? K doesn't have units, remember? No units for K. Okay. The other thing you can do is you can always multiply coefficients by a number, divide coefficients by a number, right? But this time, when you do those changes, here's how K gets affected. If you multiply, do I have a good example in here? Let's see. Okay, so here's the basic rule, right? If you change the coefficients in your K expression, that means you're changing the what? You change the coefficients, when you write your K expression, you're changing the exponents, right? Because that's where the coefficients go in the K expression, don't they? Coefficients are the exponents. If you change the coefficients, you're changing the exponents. So if you have an original K value, right, but then you change the coefficients, you got to take that K value and raise it to that exponential change you made. Look at number 12. Okay, here's an equation. It has a K value, and you're like, Ms. Poe, you forgot to put the number. No, I just meant to give you the symbol, because I don't care what the number is. Whatever the number is what it is. What did I do to my equation between what I gave you and what I'm showing you? What did I do? I multiplied each coefficient by 3. Yes? Multiplied by 3. That means this new reaction value of K, right? So sometimes we use this little like prime symbol. So if this is my new reaction, right? Maybe I'm talking about K and this is for my new one, right? Or you could put a 1, or you could put, but like a prime symbol is quite often used. Yeah, it's a way to denote it's different from the other one. Yeah, it's a different K from the other K. Yeah. What is this K's value? Well, I can take the K I was given and do what to it? Not multiply it by 3. Cube it, right? I cube it. So I cube the original K value. Do the same thing. And then lastly, what if?
So
Mm-hmm.
it would just be that
original number cubed. Cube the number.
Okay.
That number raised to the 3rd power. Cube the number. And then lastly, this is kind of like Hess's law, okay? What if I ask you to find K for a reaction using a system of other reactions. Look at 13. Look at 13. You need to manipulate your system of equations to add to give the overall that you're looking for. Manipulate. You are going to manipulate. What are two manipulations you can do? You can do write it reverse or forward, and you can change coefficients. That's your two manipulations, right? What do you do with your K values now? Change your K values once you've manipulated. If you change something in the equation, change the K value. How do we then, when we are adding, okay, when we're adding our equations together, what we do is multiply our manipulated K values.
So I guess there's a different K value for every manipulation you make, correct?
Yeah, but you can, yes, every time you do a manipulation, that is changing K. And if you do multiple manipulations, you got to do all of the different K manipulations as well. Hang on. Okay. Look at an example, and you'll understand what I'm saying. I promise. Look at the example. Sure. Look at 13. Look at 13. Here's what I want. Here's the reaction I want K for. Right? Sometimes I call this the overall. It's the one I want to know what K would be for this reaction. What is K? Hydrogen plus carbon dioxide makes carbon monoxide and water. And this is water in the gas phase. Okay. All of that's a gas phase. I want to know what is K. Here's two equations you can manipulate. Here's the first one. Cobalt 2 oxide plus carbon monoxide makes just plain old cobalt element plus carbon dioxide. And what am I told? What do I know? K is 490. Here's another equation. Still got that cobalt 2 oxide, but now I'm seeing how it's reacting with that hydrogen, right? Well, it's still giving me just cobalt metal, but now it gives me some water vapor. And that has a K value of 67. This is, you remember, just like Hess's law. My two equations, I have to flip or not flip, or multiply or not multiply coefficients in order so that when I add equation 1 plus equation 2, I get this written exactly this way. H2 on the left side plus CO2 on the left side, right? Equals that on the right side. So pick a piece to start with. Let's look for that H2 first. Which equation has the H2 in it? The second one. Is it on the correct side of the arrow? It is on the left side. Do I only have one of them, which is what I need? Okay. So maybe I don't need to do any manipulation to equation 2. Let's see what else I need to have. Okay, I gotta have carbon dioxide on the left. Carbon dioxide shows up in equation 1, but it's on the wrong side, the way it's written. So I'm going to write it in reverse. I'm gonna write it in reverse. Which means I do what? I write the solid cobalt plus the CO2 makes cobalt 2 oxide compound. And what was the other thing? Carbon monoxide. Okay. But what did I do? I'm looking at this equation in the reverse direction. What does that mean about that K value? The K for this way it's written is not 490, it's what? 1 divided by 490, right? Equals whatever that is. Okay, so now when I add these two equations together, like when we were adding mechanisms, what things are identical and are going to cancel on either side of the arrows? The solid cobalt oxide and the solid cobalt. Gone, right? That leaves me with what? Hydrogen plus CO2 makes carbon monoxide plus water. Gas. What do I do down for K? What is this K value? How do I get this K value? Do I add these numbers together? I multiply. I multiply the K's for each equation together. Multiply. What is that? .00204 is whatever that is. So I'm going to multiply that K times that other K. What is K for this overall reaction? 0. I guess we should do 2 sig figs, yeah? 0.14? There you go. There's a way you can find K. You've got some equations for it. All right. Okay, y'all take yourselves a nice little break and head down to lab. I got to print the lab paper for today. So you, your second chapter 13 homework set over equilibrium calculations. like the quadratic and type 1, 2, 3, and a little bit of this manipulating, do Wednesday night. Okay. Do Wednesday night. And then that equilibrium problem set lab worksheet that I gave y'all, right? I mean, probably also do Wednesday. Okay. You mean like this? You mean the equilibrium types, type 1, type 2, type 3. There's, I think what I ended up doing for just that worksheet is the first page is like Le Chatelier's principle stuff. And then the second and third page are one or two examples of each type. I don't quite remember how many I did, but there's a regular type 1 where you just plug and chug, and then there's at least 2 or 3 with an ice table. And I think there's only one where you have to use a quadratic, but you can make the simplifying assumption to make the assumption. Yeah, I thought, so anyways, okay. Okay, so again, like I said, take a little break, go down there, and I'll print the labs, and then we'll come down and talk about it. We're gonna look at Le Chatelier's principle today. So no math today. Yes. Hallelujah. No math today. Instead, yeah, we can go home and do math. Instead, we're gonna look at teapots and shifting equilibrium and stuff, right? Okay.